In this video, we will look at a common physics example, the Atwood's machine. Historically, this machine was used to measure the acceleration due to gravity little g through an indirect means through a machine that accelerated at a rate slower than g, so it was easier to take measurements. For our purposes, it serves as a great tool to see if you can combine multiple physics principles together, which is why we're primarily interested in it. Here's the idea. We've got a pulley here. This pulley is both massless and frictionless. That means we don't really need to worry about anything that the pulley does besides have this string over it. And this string, the two blocks are attached to the same string. This one has mass capital M, this one has mass lowercase m, and capital M is greater than lowercase m. As a result, this block will accelerate downwards and the other block will accelerate upwards. And so we're going to determine the acceleration of this system, which will be in terms of the two masses and fundamental constants, which for our purposes means little g. I will, I'll give you two tips to make this happen, and I will show you how to do it. First, we'll notice that the acceleration of the block upwards must be the same as the acceleration of this block downwards because they're connected to a rope. So that's the first thing we might want to write down, is that the acceleration of block 1 is going to be equal in magnitude to the acceleration of block 2, and so we will just call that A. Next, we're going to choose our system or systems. Here, we actually want to choose two separate systems. We want to choose the system that consists of block 1. We'll call that system 1. And we want to choose the system that consists of block 2. We'll call that one S2. I'm going to give you two tips for solving problems like this where there are two objects that are connected in some way. And here's tip number 1. For each system, I want you to choose the positive direction to be the direction of the acceleration. To be the direction of the acceleration. That's not necessarily the same as the direction of the velocity, though it will be in this case, because we're going to say they start from rest. What does that mean in practice? It means that system 1, the positive direction, should be downwards, because this heavier block will accelerate downwards. For block 2, the lighter one, it will accelerate upwards. So the positive y direction for system 2 should be upwards. Let's now, I'll give you the overview of what we're going to do. We're going to apply Newton's second law to each of these systems after drawing a free body diagram. And then we'll get a system of two equations which we will use to solve for the acceleration. Let's first look at system 1. The free body diagram for system 1, we're going to take that block and shrink it down to a single point particle. And we'll observe that there's a downward force that the Earth exerts on system 1, and there is an upward tension force. What's pulling at the other end of the string? Oh, it's system 2, so that's the tension that system 2 exerts on 1. We'll also note that this tension must be less than the gravitational force because the acceleration is in the downward direction. Since the acceleration is down, that means the sum of the forces must also be down. And we'll keep that sort of in the back of our mind. System 2, we'll take it and shrink it down to a single point particle 2. It has the same magnitude of tension upwards because this is the Newton's third law pair. This is the tension that system 1 is exerting on 2, which must be equal in magnitude to the tension that 2 exerts on 1. So these are the same through Newton's third law. The gravitational force that the Earth exerts on 2 must be less than the gravitational force that the Earth exerts on 1 because it has less mass. But also this gravitational force must be less than the tension force on system 2 because overall the acceleration for this system is up, which means that the sum of the forces must be in the upward direction. And then we'll throw off to the side here that T2 on 1 equals T1 on 2 by Newton's third law. And with that, we are ready to write Newton's second law for each of these two systems. We'll start with system 1. the sum of the forces in the y direction for system 1. Let's see, down is the positive direction, so that'll be the force that the Earth exerts on 1 minus the tension that 2 exerts on 1, and that's in the negative upward direction for that system. And that's got to be equal to the mass of system 1, which we called capital M, times the acceleration of the system. Now, system 2, the sum of the forces in the y direction for system 2, well, that's going to be up is the positive direction, so the tension that 1 exerts on 2 minus force that Earth exerts on 2 is in the downward negative direction for that system. And that's got to be equal to m times lowercase a. Both of these accelerations are positive by definition, or by choice. We chose the positive direction to be the direction of the acceleration, so these both become positive. All right, simplifying each of these just a little bit. I'm going to replace the force that the Earth exerts on 1 and 2 with mg. So this is capital mg minus tension 2 on 1 equals capital Ma. And then over here, tension 1 on 2 minus lowercase mg equals lowercase ma. Now there's two unknowns. Unknown number 1 is this tension, which we said was equal by Newton's third law. And the other unknown is the acceleration. And that's the same because they're connected by a rope. We know, are able to measure everything else, right? We can put the masses on scales, and we know little g is 9.8 newtons per kilogram on Earth. The one that we don't want in our final answer is tension, because that wasn't in our list of allowed variables. So we're going to use substitution to eliminate tension. To do that, we will solve one of these equations for t, and then substitute that value into the second equation. What is that going to look like for us? Let's look at the second equation here. Let's get this tension by itself. This equation becomes T1 on 2 is equal to little m times A plus little m times G, adding this mg over to the other side of the equal sign. Now this expression must be, undo. Switch out highlighters here. This expression we said is equal to this tension. So we can plug in Ma plus Mg for tension 2 in that first equation, which is what we're going to do now. Capital Mg minus this whole expression, lowercase ma plus lowercase mg, that's this tension, is equal to capital Ma, keeping our highlighting convention alive for just one more line, so we can see that these are all those same tensions. Distributing that negative, we get capital Mg minus lowercase ma minus lowercase mg equals capital Ma. We are now ready for pro tip number 2. We're trying to solve for acceleration, so we want to get all terms that have an a in them. Get all terms with an acceleration term a on one side of the equal sign. So that's pro tip number 2 to keep in mind. What does that look like for us? In this equation, there are two terms that have a, little ma and big Ma. We want to add that little ma over to the other side, and that should do it. Minus ma plus ma, those two add up to 0, and we are left with big Mg minus little mg equals big Ma plus little ma. Now, why did I want to do this tip 2? Why do I want to follow that advice? Because now I can factor out that a, which works for getting it by itself on one side of the equal sign. We need to factor out the a so that we only have 1 in our equation. And that leaves us with big M plus little m. Check that if we distribute that a back in, that we end up at the line before. And now here I notice that I can factor out a little g. So I'm going to go ahead and do that. You don't have to, but it helps make things look nicer. So our last step then is to divide each side by big M plus little m, the sum of the masses. and we get that this coefficient on A, big M plus little m, cancels out, and we are left with an expression for the acceleration A equals big M minus little m divided by big M plus little m multiplied by little g. We should do a few things. We should do a unit analysis here to make sure that the units match up. On the right-hand side of this, we have units of meters per second each second. It's an acceleration. On the right-hand side of this, we have a kilograms minus kilograms is going to be units of kilograms in that numerator, divided by, let's see, kilograms plus kilograms is going to be units of kilograms in that numerator. And we know little g does have units of newtons per kilogram, which is equivalent to units of acceleration. And so these units cancel, and the units do match up. So our equation's looking good using unit analysis. We can also look at a limiting case to see if this equation makes sense. What would happen if we took the little m, that small mass, and made it go all the way to 0 kilograms? Well, that would be the equivalent of just cutting the rope, right? There being no small mass at the other end. And if we do that, then the big mass should just fall with an acceleration of little g. It should have that free fall acceleration. Is that what happens? Well, let's take a look at our equation here. The acceleration in this limiting case would be big M minus 0 over big M plus 0 times little g, which would be equal to big M over big M times little g, which is indeed just little g. So our limiting case analysis also gives us some confidence that we have derived an appropriate expression for the acceleration of an Atwood's machine. We have the appropriate acceleration for the acceleration of an Atwood's machine. I hope this video helps. If you have any questions, please don't hesitate to reach out.